Professor Warwick.
Welcome to Cybernetics at the University of Reading. Got a lot of exciting projects on the go at the present time. I'd like to show you some of them. Please join me. Hello, I'm Kevin Warwick, Professor of Cybernetics at the University of Reading. Some of you may wonder what cybernetics is about. Well, it's actually linking humans and technology together. Modern examples, particularly to do with people with disabilities, using technology to help the person overcome their disability, maybe a walking aid or even artificial legs. But nowadays there can be a lot more, can be to enhance the person, to actually make them more intelligent, give them new physical abilities. And that's particularly true today, where the technology can be integrated, perhaps even implanted with the person. Back in 1998, I had this little device. This is a radio frequency identification device, commonly known as RFID, implanted by a doctor in my left arm, just at the top of my arm, a nice fleshy part there. What it actually did was identify me to the computer in the building here at Reading University. So as I walked around, the computer could pick me up at different points. What it did was open the door to my laboratory for me, because it knew it was me, switched on lights, even said, "Hello, Professor Warwick," when I came through the front door. So we were showing what was possible with an implant like this for intelligent buildings, how the building could respond to you, but all sorts of possibilities for the future. Maybe you won't need keys for a car, maybe you won't need a credit card, maybe you won't even need a passport. A little implant like this will be all that's required to identify you to the world outside. Another one of the things we were looking at for the implant experiment was trying to increase the range of sensory input to humans, extra senses if you like. What I've got here is a baseball cap with ultrasonic sensors on. These are sonar sensors, a bit like how a bat senses the world. Now, for the implant experiment, the output from these sensors was fed down onto my nervous system. So essentially my brain was receiving pulses of current that increased in terms of their frequency the closer I got to an object. So as an object came closer to me, these pulses of current were ding, 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 ding in my brain. And as an object got further away, so the pulses died away. With a blindfold on, I was able to move around and detect where objects were, how far they were away from me, pretty accurately. Now just to demonstrate that, if I switch this on, there we go. What we're doing now to show what's possible is taking the ultrasonic signals and converting them to these little buzzy vibrations. As I'm holding this, it's vibrating, but it's making a buzzy noise. And as something comes closer, so if you can imagine these signals not being buzzy vibrations in my hand, but being signals in my brain, it means it's an extra sense. Those signals, not buzzing, but pulsing in your brain, are used by your brain to detect objects, how far they are away. Pretty clearly you can see how as objects get closer, it's affecting the vibrator here, but affected my brain via the implant. It gave me an extra sense. The last implant that I had, this little device here, very, very small, it's got 100 pins, 100 electrodes. Each of them is 1.5 millimeters long, so it's very, very small. This was fired into my nervous system, the nerves in my left arm, the median nerve fibers, and it was in there for just over 3 months for the purpose of the experiment. What it did essentially is a bit like putting an electric plug in a socket, but instead of 2 or 3 pins, there are 100. But it made a direct electrical connection, so that every time I moved my hand, the neural signals, the brain signals that did that, we could pick up via the implant in the computer and then send the signals somewhere else, so that my neural signals could control a robot hand, for example. But also when signals were passed into my nervous system, my brain could recognise the pulses. So the robot hand has fingertip sensors on it, for example, and hence signals from those sensors could be sent onto my nervous system that my brain could recognise. Now we're doing it partly for looking at could we help people with disabilities, someone who's lost their hand or somebody who's perhaps paralysed who can't move in some way. Could we pick up neural signals in some part of their nervous system or their brain and use those signals to control technology? And also, could we send signals in to look at extending the range of senses that a person has?
Hello, Professor Warwick.
With the implant in my nervous system, I had wires coming out of my arm and we needed to connect up to the outside world. So the wires actually connected to this green connector pad. The terminals here, therefore, were linked directly into my nervous system via the implant, which meant that I had to make sure I didn't get any water on these terminals for the 3 months. But it also meant we could link up via this little radio transmitter receiver unit so that when I moved my hand, my neural signals were sent to the computer, but also signals from the computer transmitted the other way to stimulate my nervous system. One of the experiments that was very successful was linking up to the robot hand that we see here. The big thing was, though, that I was in New York, in Columbia University, in their real-time computing labs, and the robot hand was back here, University of Reading in England. So when I moved my hand in New York, my neural signals were sent across the internet to move the robot hand in Reading, in the UK. So the robot hand was mimicking my hand movements. Based on my neural signals. My brain signals were controlling the robot hand. As the robot hand gripped an object, the little sensors on the fingertips of the robot hand put pressure on the object, and signals were sent back from those fingertips across the internet to stimulate my nervous system. So as the hand gripped an object more and more, my brain was receiving an increased frequency of current pulse. So essentially, as the hand gripped more and more, so my brain was receiving ding, 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 these pulses of current that increased the more force the hand was applying. So on a different continent, my brain was able to feel the force that the robot hand was applying 3,500 miles away. When my implant was connected to the robot hand, so my nervous system was actually plugged into the internet in real time. Now it was great for controlling the hand, and of course it opens up possibilities for people that have had their hand amputated, maybe to control a hand like this instead of their original hand. It also, of course, extends the nervous system. It extends your body into all sorts of dimensions that we haven't dreamt of before. But it does open up other possibilities, some of them not so positive. One is, of course, when your nervous system, when your brain is plugged into the internet, there's the possibility of stray signals, maybe even people hacking into not just your computer system, but hacking into your nervous system and hacking into your brain. So you get the possibility of software downloads, which could help medically, but also software downloads that could cause problems, software viruses that ultimately become biological viruses. One thing I've always been interested in is intelligence, not just in humans, but in machines, artificial intelligence, if you like. And we've got some examples here. This is a little robot, which I'm going to switch on in a second, bring it to life. It has a neural network, an artificial intelligence system that controls it in terms of making its decisions. Now, what it is supposed to do, this robot, is to move around in the little corral that we have here and learn over 3 or 4 minutes how to move around without bumping into the wall. But as we'll see, when we switch it on, it will actually make a few mistakes to start with. But hopefully 3 or 4 minutes into its life, it should be a little bit better. But we can't tell because it's a brain and it's learning how to move about. So off it goes. And I'll be happier if it does bump into something soon, because then it can learn what to do so it doesn't bump into something. When it gets to the wall, it can move backwards, but moving backwards is not moving forwards, which is what it's supposed to do. So it's like a contradictory behaviour that it has to get used to. This actually is not making the sort of mistakes I would like. So I will switch on another couple of robots. These are doing exactly the same thing. So we have 3 robots now moving around. Let's let them learn. These robots actually are quite a serious research base. We can learn the type of artificial intelligence that works in a practical environment by testing it out on the little robots here. One example of actually using it in practice comes with this device. This is actually a power pack and the electronics for an implant which is used to help people with Parkinson's disease. Now what we're trying to do is to make the implant intelligent so that it can actually predict when somebody is going to have a tremor, the typical Parkinsonian tremor, and then stop the tremors occurring before they actually start, in terms of injecting an electronic signal deep into the person's brain. So what we're doing with the electrodes is monitoring the activity in the person's brain and using an artificial intelligence system, a neural network, just like the ones on these little robots, this time though to predict accurately when somebody is going to have a typical tremor start with Parkinson's disease. The same sort of prediction we're now looking at using for people with epilepsy. So with implants in the person's brain, we can use an artificial intelligence system to predict when the person's going to have an epileptic seizure. So these are ways that we research with little robots like this. Can be a bit of fun, but it's serious research, but then use the output of that research to actually help people directly, this time in the medical environment. Literally help people live, help people move around.